Let's go ahead and find the derivative for the natural log of x. So the claim here is that if f of x is equal to the natural log of x, then f prime is equal to 1 over x. Okay. Now, this is actually quite easy to do with the power series and, well, actually not power series, a Taylor series. Okay. Ln x is an analytic function, okay, but it does have a pole at 0. But we can shift it out of that pole and we can find a nice Taylor series expansion of that. Okay, we can take the derivative term by term and then condense that again and show that that's equal to 1 over x. So just food for thought in case you're interested. Maybe one day we'll make a video on that. But we're going to actually just use the limit definition as we become accustomed to doing. This is the purest way of proving calculus statements, so that's what we're going to do. Okay. We'll have to think along the way what it is we're going to do. It seems a little challenging, but we're going to get through it. So f prime is equal to the limit as h trends to 0. So we're going to have the natural log of x plus h minus the natural log of x over h. Okay. Well, we've got log properties. I can already tell what I'd like to experiment with here. We got the limit as h goes to 0. And we're going to write this as the natural log of x plus h over x. Okay. Let's not forget that's still multiplied by 1 over h there. Okay. All right, let's take a close look. Now, the natural log of 1 is 0, but that's not going to be a problem. As h goes to 0, this goes to x over x, which is 1. The natural log of 1 is 0. But that won't be a problem there. Okay, we just have to worry about it being undefined in certain places. But typically, we don't have to worry about that since the limit is not concerned with what happens at, but what happens near as we want, in fact. Okay, let's think about defining this as follows. The limit as h goes to 0, we'll go ahead and take the 1 over h, put it on the left-hand side. This is going to be the natural log of 1 plus h over x. Okay, obviously, right? A plus b over a equals a over a plus b over a equals 1 plus b over a. Just using some simple algebraic property there. Okay, which I suppose we take for granted. We shouldn't. This is true because of the definition. We define it this way. Okay, study abstract algebra if you'd like to know more about that. Maybe one day we'll make videos on that. Okay, just an application of the distributive property when you think about it. It's just 1 over a times a plus 1 over a times b. Why do we define the distributive property the way we do? Well, because it helps us. And a binary operation distributed across another binary operation is a necessity for a ring. Okay, and later on we'll again maybe discuss groups, rings, fields. They're different groups, different rings, right? Abelian groups, right? Commutative rings, non-commutative rings. Anyway, we're getting ahead of ourselves. Let's get back to the proof. Well, interestingly, I can take this and bring it up. That's something I can do. I don't know if that's something I should do. Let's experiment with it. Let's see where it brings us. It's going to give us the limit as h trends to 0, the natural log of 1 plus h over x, all raised to the 1 over h power. Okay? Now, I can already see what this is leading to. This is starting to look a lot like the definition for E. Over here, I'm going to provide a couple definitions. So we've got E is equal to, not just approximately, but equal to the limit as h goes to 0, okay, of 1 plus 1 over h to the h, okay. No, nope, misspoke. 1 plus h to the h, there we go. No, there we go, okay. But we have an alternative definition. If I just think about reciprocating this, and then instead of going to 0, going to infinity, I have the limit as h goes to infinity of 1 plus 1 over h to the 1 over h, which is just h. Okay, so these are definitions of E. Okay, and I want the viewer to note that I got something very similar going on here. I'm just going to need to use a substitution essentially. So we're going to let u equal h over x. Okay? Notice that the limit as h goes to 0 of h over x equals 0, but it's also equal to the limit as u goes to 0 of u. Okay? Again, this is equal to this. So I can swap out those limits. This is the same thing as the limit as u goes to 0. Limit as h goes to 0 is the same thing as limit as u goes to 0 of the same thing. So now I'm going to have the natural log of 1 plus u to the 1 over, what is h? H is ux. That's right. H is ux. Oh yeah, and we're done. Because this is just, oh yeah, that's nice. Look at how this is going to work out. This is going to give us the limit as u trends to 0 of the natural log of 1 plus u to the 1 over u times 1 over x. Okay, just splitting apart these powers. And now I'm going to use the power rule in reverse to bring the 1 over x down. I got the limit as u trends to 0, 1 over x times the natural log of 1 plus u to the 1 over u. We know that the limit of a product is the same thing as the product of limits. We also know that this limit is not dependent on x. I can bring this whole 1 over x out. I have the 1 over x times the limit as u trends to 0 of the natural log of 1 plus u to the 1 over u power. What is the limit as u goes to 0 of the natural log of 1 plus u to the 1 over u? That's just e, or the natural log of e, excuse me. And the natural log of e is just 1. So I'm going to have 1 over x, excuse me, of the natural log of e. Natural log of e is 1, so this is 1 over x times 1, which is 1 over x. Okay. That's interesting. Not very challenging, with a little bit of experimentation and some confidence, right? Proceeding through this with confidence. Of course, you got to know your definitions, right? I think with natural log, you can expect in a proof to maybe convert it to its exponential variant. In this case, it just cancels out. E to the x and ln of x cancel each other out. Hopefully you enjoyed that. Hopefully that helped you. Let me know if you have any questions. We love proven math around here. All sorts of statements, including statements from physics and any other discipline that requires rigorous analysis. Look forward to seeing you in the next videos. Until then, enjoy the math. Take care.